Howdy, everybody. Hope we're doing well. Today, we're going to pick up where we left off and talking about research methods. But like I mentioned before, we are going to focus specifically on the research method of an experiment. And just like I said 225 million times, we focus so much on the experiment because it's unique in that it's the only research method in which you can prove causation that a change in X variable can cause a change in Y variable. So, we're going to look at the components of good experimental design. So, these are the things that you need to be doing. So think about when you did the science fair or something in like elementary school, middle school. These are the things that you need to do in your experiment to make sure that it is actually a good experiment and that your data is valid and that it really is proving causation. So, these are all the things that you need to do as an experimenter in order to make sure that this is happening. So, first, we said, of course, we need a hypothesis, right? What's an experiment without what the question you're trying to test and answer? So, that if then prediction. How the hypothesis typically is set up is that your if is the independent variable, and then after it, the then is the dependent variable. So, hypothesis of here we have Dr. Sanchez thinks that if students are in a classroom with intense lighting, then they will have improved academic performance. And we have to explain what intense lighting means, but we can say for this purpose, it's like overhead lighting rather than what I have with the chill dim lighting. So, right, if independent variable is the type of lighting, then this will result in students having better academic performance. The independent variable changes, and the dependent variable should change as a result of the independent variable changing. So now, a key word to note is manipulation of at least one variable. And this is when I talk about key terms to know for the different research methods. If they were to ask you on an FRQ, is this an experiment? Why? Yes or no? If you can say there was manipulation of the independent variable, then you got it. That's your point. So you need to say that there's manipulation of the independent variable. And that just means manipulating, it means you're changing it. So you change the independent variable. In this case, you are changing the independent variable of lighting, right? Some people are getting chill low light, and then other people are getting the intense fluorescent overhead lighting. So independent variable is the if, it's what the researcher changes, and then the dependent variable is the then, just like I said. Um, so if you can point out that there's manipulation of variable in which an independent variable is being changed, then you are good to go in saying that this is a real deal experiment. But like I said, in my first one, we talked about lighting, and we need to what we call operationally define what that lighting is. Like what is considered intense lighting or what is considered low lighting. Like we have to kind of define what that is so we know an experiment to be clear and clear all across the board so it can be replicated. So we're gonna come back to operational definitions, but what we're gonna do is first talk about how to make a peanut butter and jelly sandwich. So if you're home, you can go ahead and write down your little step-by-step instructions on how, if you were to tell a little kid, you're describing to them for the first time how to make a PB&J sandwich. So write down those instructions, and we'll see here. These are from last year, but we find that it's really important to be very clear in how you are defining things and very precise in the directions you're giving. So, for example, if you just say, go get some bread, okay, well, am I getting a baguette or am I getting sandwich bread? Or you say to get the knife to spread it. Okay, am I getting a steak knife? Am I getting like a little cheese knife? Or am I getting a butter knife? Right? So this is where operational definitions come into play. And you can watch this good video here to see more of what I'm talking about. But this is where operational definitions, we see the importance of them in that we need to operationally define our variables. So, because like I mentioned the other day, we want a study that is replicated, a study that has been done and tried again and again and again by researchers all over the world and are getting the same results. Because think about if you're doing vaccine research, a research on some kind of medication. I wouldn't want to take a medication or a vaccine that has not been replicated and tested on, by different people around the world. Like, how do I know that it works? So that's the same thing with any kind of psychological research, right? You want it to be replicated. And in order for your experiment to be, your study or experiment to be replicated, it needs to have really precise operational definitions of your variables. So that way, when you're talking lighting, Joe Schmo in New York City and Billy Sue in Australia can have identical experimental setups, right? If the independent variable is the type of lighting, you're operationally defining what it means to be intense lighting in that group, and then what it means to be low lighting. So that way you can replicate it. So operational definitions are just kind of being specific in how you are describing your variables. So you need specific and precise operational definitions of all the important things you're studying. So here's another example of a research study. So I like this one. People who eat ice cream frequently will have a more positive mood. So think of the hypothesis. If people eat ice cream more frequently, then they will have a more positive mood. So we need to operationally define lots of things. So what does it mean to frequently eat ice cream, right? Again, Joe Schmo and Billy Sue across the world need to have that same definition to know what is considered frequently eating ice cream. Is it eating ice cream like every single day, or is it eating ice cream just like 3 times a week, right? We need to have the same definition in order to have our studies be the same. We also need to figure out what ice cream is because, y'all, and when I worked at Culver's in Illinois, a lot of people didn't know that custard's different than ice cream, and those are very different things, in my opinion. So we need to operationally define what is ice cream so we know that we're all giving the same thing, right? If you're doing this with Andre in Italy, they can't be giving out gelato. All right. And then we said that our dependent variable is mood. And oftentimes in AP, they ask you to operationally define the dependent variable of most things. So remember, independent variable is the first thing, what you're changing. Dependent variable is what changes as a result. So in this case, dependent variable is the mood you'll have. So we need to operationally define what does it mean to be in a positive mood. So you need to say, how are you measuring someone's mood? Are you measuring it by seeing if they smile? Are you measuring it by having them self-report out and like saying, I'm happy? Or are they taking like a survey and they get a mood score of like an 8 to 10? So you need to say, really with operational definitions, it's kind of how are we measuring the dependent variable is another way to phrase it. So in this case, right, I said you are measuring your mood by self-reporting on a scale of 8 to 10 on what I called the mood indicator analysis test. And then you also need to operationally find like who are the people. So is it anybody involved in the study, or I said it's people ages 21 through 60? Because again, we need to know who the population is so Billy Sue can go replicate it in Australia. So your official definition of operational definition is the statement of precise procedures the researcher is going to use in order to measure a specific variable. And again, anytime you look at a research study that AP is going to give you, oftentimes they're going to ask you how do you operationally define the dependent variable? So you're looking at how are you going to measure the dependent variable? How are you going to like see how it's changed? So in our Dr. Sanchez example with lighting, we said measure the intensity of lighting in a classroom will impact students' academic performance. She gives students in each condition a 10-point standardized test to complete. Right? So they are measuring the academic performance, which is the dependent variable, right? It's changing as a result of the lighting, the independent variable. So they're measuring academic performance by seeing how they do on a 10-point standardized test, right? We need to figure out, we need to all have the same thing, that everyone should be receiving the same 10-point standardized test to assess um, their academic performance, right? You need to specify, are we looking at their GPAs? If they go up over time, are we looking at how they do on a test? Are we looking at their classroom participation, right? You need to all be on the same page in how you are assessing or measuring their academic performance, that dependent variable. So, right, the AP will ask you to identify the dependent variable and then operationally define it. So, academic performance, and then their score on a standardized 10-point test. So, like I said, the whole point of this is so we can replicate our research. And I said, I don't want any medicine or vaccine or whatever that has not been replicated multiple times on different populations. Um, so, right, I did a Scavone study in Oconomowoc and found that people who eat more ice cream tend to have a better mood. If renowned psychologist Dr. Joe Schmo were to replicate the study in Thailand, would it get the same results? And we know that sometimes they might not, because you think of different cultural preferences and norms, socioeconomic status, education levels, gender. We know there's plenty of things that might cause there to be different results. But this is why it's really important to replicate research. Does this only hold true to like one particular population? The issue with psychology that we often see is that the population they research with are like now maybe a little more diverse, but often like white male college students in the United States. So you're missing out on like so much of the greater world. And that's kind of a lot of the issues with traditional psych studies, especially done in like the 60s, 70s, is like how how applicable is this to everybody? Um, so we need to replicate and take our studies and do them and see if they hold up elsewhere. Okay. And like I said, replication will show if you are getting the same results of your study over and over and over again, then it's reliable. It's going to be a fairly good study. Okay. So then another component of a good experimental design, and again, something that if an FRQ tutor asks you, hey, you read about this study, is it in fact an experiment? And you see that there's a control and experimental group, you got it. And the first day of school, when I showed you the vocab packet example, I think my student gave the good example of um, often they do, unfortunately, animal testing on little rats, often with makeup brands and cosmetics and whatnot. So we said the control group is the group that does not receive the treatment or the independent variable. And then the experimental group is the one that does receive the treatment or the independent variable. So experimental group is the one that's exposed to the change. And that's why it's the experimental group, right? Um, so in the case of the animal experimentation with cosmetic brands, I think my student said that the control group is the one that doesn't get makeup put on them. The rats are normal. And then the experimental group is the one that's getting the makeup and whatnot put on them. They're the one who are exposed to the change. So if we go back to our example of the light one, so um, if your classroom's normally, if my classroom's normally dim, um, right, that would be the control group. And I'm introducing a change to see if I make my lighting more intense, if that's going to improve academic performance. So the group that's receiving the change and that I'm now turning on the overhead lights, that would be the experimental group. Or in my case of ice cream, ice cream's impact on mood. Control group would live their life normally. They wouldn't be eating more ice cream. And then the experimental group, because we're seeing the impact of ice cream on your mood, the experimental group would be the one getting ice cream. So you always need an experimental and control group so you can compare your findings. And let's take the example of a vaccine right now, because that's what's relevant. Right? We would not want a vaccine that was not tested amongst a control group, right? Because how do you know if your vaccine's effective if you're not comparing it against people who didn't receive the vaccine, right? Like, are people who um, receive the COVID vaccine or people who didn't receive the COVID vaccine getting sick or infected or whatever at similar rates to the experimental group? If you don't have a control group, like, how are you going to know if your thing's effective or not? Okay, then Another important component of experimental design is controlling for confounding or third variables. And remember, yesterday we talked about that issue of the third variable problem, in which originally it looked like eating ice cream was causing sunburns, but we really realized there was this third or confounding variable in the background that was actually causing that relationship, which was the sun or it being hot summery day, right? So a confounding variable is kind of like this third variable thing. It's an extra variable that you didn't account for. That's not the independent variable, which is creating a change in the dependent variable, right? So if your study was on ice cream, independent variable, and then dependent variable being the sunburn occurring, we said that the third variable or the confounding variable is the sun because that was not the independent variable you intended that you were researching for, but it was something that you didn't plan that was going on in the environment in the background that you didn't control for that now messed up your experiment results, right? Because you didn't actually see if it's the ice cream that's causing your sunburn. So, a true experiment is better than the correlational research because you can control for these things and make sure, if it's a good experiment and you're doing it right, make sure that everything is controlled for um, and that there is not any third or confounding variables that are interfering with your results, and that you can know for certain that there's nothing else factoring in. It is the independent variable that is causing a change in the dependent variable. So we're going to see some potential confounding variables that often happen. We see biased groups. So, right, what if you have, let's take like, I don't know, the COVID vaccine, and you have the group that's getting the vaccine and the people that aren't. Um, think about if the experimental group happens to be like everyone's really, really healthy, and then the control group is like really unhealthy people, like that's a biased grouping. Like that's not going to tell you anything because obviously the like unhealthy people in the control group are going to have worse outcomes than the healthy people in the experimental group. You need to make sure that it's completely similar. Like, well, first off, that people aren't picking their groups; it's being picked for them randomly, and that it's all similar ages, demographics, whatever. It's evenly split. So you use something called random assignment. I'm going to go over, but it's you're randomly assigning people to the control or experimental group. There's a good example in the Grey's Anatomy thing I'm going to show us in a sec, in which there's life-saving Alzheimer's treatment. So everyone wants to be in the experimental group because it's this rare drug that could really help you. Um, but we know it's not fair if people are picking or getting biased treatment and who gets this potentially life-saving drug in the experimental group. So you have to use random assignment, in which maybe like a computer generated thing is fairly and unbiasedly sorting out people evenly into the control and experimental group. We also know the placebo effect is this idea that like you think that you're getting the treatment, so you're going to you actually you're not actually getting better, but you think you're getting better just by taking something. And it turns out you're just taking the placebo, like a sugar cube or a sugar pill or something that's not actually the medication, but you think you're taking it. So you end up kind of acting differently because of that, or thinking you're getting better because of that. And that's something that also could mess up your research. So doing things like a single and double blind study, which I'm going to talk about, could help that, as well as demand characteristics, which is, I've mentioned this word a few times, when you kind of act a certain way because you know you're being observed or researched, or you try and interpret what the purpose of the experiment is and try and please the researcher and act accordingly. So act differently than you would in normal circumstances. And then experimenter bias could be that the experimenter is unintentionally pushing people to act a certain way so that it's kind of proving their hypothesis. And they might unintentionally kind of be doing this. So using a single and double blind study is something that can help you with these things. So other confounding variables, like I said, so let's just talk random assignment, right? Like I said, randomly assigning people into the control or experimental group by chance. So picking names out of a hat, using a computer generated program, whatever, prevents the experimenter from picking teams and being biased and saying, oh, I have this life-saving treatment in the experimental group. I want you to get this. That's biased. Okay, so like I said, Placebo effect, beneficial effect that happens due to person's belief they'll receive a benefit. Demand characteristics. Some examples of those are social desirability bias, which is that you answer questions to sound better. Hawthorne effect is this idea that you changing your behavior because you're being observed. Just like I said, if Curtis came in during a lesson, I'll probably act more on my game than I usually would, and you guys would as well as students. Okay. And like I said, some really good ways. So if you are asked, which might happen in a research methods FRQ, you are asked to say, how could you prevent confounding variables? Talking about using a single or double blind study is a really good way to do that. We said single blind is where the experimenters know who's receiving the treatment, so who's in what group, or who's receiving the treatment or independent variable, so aka in the experimental group, and who's in the control. Um, this helps prevent things like placebo effect, social desirability bias, demand characteristics, whatever, and controls for participant bias because they don't know which group they're in. If possible, an even better one might be using double blind because this prevents both participant and experimenter bias. And in this, both the participants and the researcher do not know who is receiving the particular treatment or in the experimenter or control experimental or control group. This isn't always possible because if you think health things like in a vaccine trial, they're going to need to know who's getting the vaccine in case there were to be some side effect or something, right? Just that's important to know. So sometimes only single blinds available, but if you can use a double blind, that's the best because it prevents both those participant and the experimenter bias. Okay. And another important part of a good experimental design, like I said, is generalizability. So, can your sample and findings be applied to the greater population? So, can you take the sample that you used in your study and say that this is applicable to everyone in your target population? So, some important terms to go over are what's a population versus what's a sample. And a population is the group that you are pulling your sample or people who are participants in your study from. So, for example, if I was doing my study on ice cream impacting mood, if I wanted to apply it to just teenagers in the United States, then my sample should be pulled of teenagers from all over all 50 states, from all over different high schools, different socioeconomic levels, whatever. So the sample is what you're pulling from in terms of the population that you're targeting for. So you need to make sure, does my sample represent my population? And if it doesn't, then you have sampling bias happening. And that's, again, something that can be a confounding variable and just not, you know, it's not going to make your study credible. So, an example of this is if my target population, I'm trying to apply my ice cream study to all of the United States, teenagers in the United States, but the population I used in my study are just um, teenagers from Oconomowoc High School. That is not representative of the greater population of teenagers in the United States. I would need teenagers from urban areas, suburban, rural, different economic status, different racial backgrounds, whatever. So that would be sampling biased, that my sample is not representative of the greater population I'm trying to apply my findings to. So, something that I could do to prevent this would be random sampling. So, this is taking every member of the population that I'm trying to apply it to and, putting it in like a computer generator, drawing names out of the hat. So, putting all their names in and then using that kind of program or whatever to make sure that it's truly random who you're picking to be a part of your study. So, let's chat about random sampling versus random assignment. So, random sampling can be used in any study. It's just who's going to be in your research. So, it's kind of bigger than random assignment. It could be used in who's going to be in your survey, who's going to be in your naturalistic observation, who's going to be in your experiment. It's this idea that each person in the larger population has an equal chance of being included in the research, right? So this prevents sampling bias and helps create generalizability. Random assignment is unique to the experiment. So if you were talking about something that, why is this an experiment? Random sampling wouldn't give you that point because anything can have random sampling, any type of study. But random assignment is unique to experiments because it's you randomly assigning your sample, right? So it's random sampling first, then random assignment. So you randomly assigning your sample into the control or experimental group. Okay. Oh, this was the example I had. All right. So here's an example of a rubric in which they're talking about you need to say why this study is an experiment. And you see that all these things score points. So saying that um, vitamin J, there was manipulation of vitamin J variable, that there was random assignment, but we said random sampling doesn't make an experiment because that can be used for anything. So you need to talk about random assignment. If you talked about control or experimental groups or placebo groups, if you talked about double, single blind, right? All those things, if you discuss them, would earn you that point in saying this is why this study is an experiment. A good lesson is from this Grey's Anatomy episode. If you're wanting help applying some of these terms, it's really good. I'd recommend watching that and kind of seeing how you could apply some of these terms like placebo effect, random assignment, control, experimental group, double or single blind, etc. So that's kind of what we got here. Yeah, so hopefully we now know what we need for a good quality experiment. Yes. Have a nice day, everyone. Let me know if you have any questions.